The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Set. Okay. So the next part today is going to be about concurrent programming. So in this lecture, we are going to study concurrent programming with the emphasis for correctness of programs, because parallel programs will have the same correctness issues. So if you want to get parallel, you better get the concurrency right first. And what we're also going to do is start with a much simpler machine model and a program model. We are going to use Java because I think a lot of people understand Java. Also, we are going to use a very simple shared memory machine abstraction. I'm not going to even talk about any machine anymore. I'm just going to talk about concurrent programming here. And you need to get through this one before you can start digging deep into the next level. Come on. Oops. So in the next lecture, we will switch from Java to C, C++. I guess you're using MPI, Roderick, MPI primitives in here. And we'll start moving into parallelism with emphasis on performance. And of course, you have to get correctness, that's given, but we'll start looking at performance in there. And we'll start using the distributed memory machine, all the notions and details of cells. So we'll just kind of go down and down in that direction. So what's concurrency? Sequential program is, look at sequential program, opposite. It's basically single thread of execution. You execute one, finish that, go to the next, and go to the next. That's a very simple abstract model. Then for about 35 years, 40 years, none of the machines were actually following that. They had things in the back that actually had some parallelism. A concurrent program is at the shared memory level, we can say it's a collection of autonomous sequential threads executing logically in parallel. So you can execute this thing either multi-programming, so you can multiplex different parts on a multiprocessor, or multiprocessing, basically have each thread running on different machine, or even distribute. You can actually send it to threads to different places. Of course, you have to deal with memory issues in here. So concurrency is not only parallelism. So if you can do interleaved concurrencies, you can have logically parallel, but you run thread A for a while, context switch thread B for a while, context switch thread C, so you can have multiple threads on the same machine running. Or you can actually have running parallel. You can have 3 different machines running A, B, and C all the time. So you can have both in there. But logically, you should not see a difference except for performance and stuff like that. So what I'm going to do is do a bunch of examples. So can you read this? Okay. Let's start with a bank. So you have a bank account. So in Java, you just basically have ID, password, and balance. And you have some way to construct this object in here. And you can see whether the password is correct. You can get the balance. And you can post the balance. So that's a very simple account object. And if you have a bank, you have a bunch of accounts in a hash map. And you create the hash map in here. And then you can basically say get the bank. You can actually create a bank in here. And you can get an account given an ID, basically. Now assume you want to build an ATM. How do you build an ATM? So you have a bank. You need a bank in here. And you have some input and output streams in here. And when you start ATM, you will set up this input and output streams in here. And the main function, what you'll do is you'll get a bank, create where the input streams are coming from, create output goes standard system out, output goes there, and create an ATM in here, and you let the ATM run. So how do you run the ATM? So what happens in run is you run forever. ATM doesn't stop anytime. And what you can do is you can ask when somebody walks into ATM, you can say, what's your account ID? You type the account ID. So, and you can get the account. So of course, if the account ID is wrong, it says it will throw exception. You can say, okay, what's the password? Get the password. You check the password. If it's wrong, you throw exception. And then you can say, here's your balance today. What do you want to do? How do you want to? If you want to withdraw or deposit, and you can, if you want to withdraw, you can give minus number. If you want to deposit, you give a plus number. and then you can post that into your balance. Everybody got the simple ATM? So assume activity trace. So somebody comes and gives the account ID, Alisa gives the password and says they're $1,000 and say how much you withdraw, 200 withdraw, and you get the balance in here. Looks nice, it works. So I need to run multiple ATMs. Assume I am in a place that I actually want to put 2 ATMs or 4 ATMs next to each other, ATM things in there. So how do I go and do that? So in order to do that, there's a concurrency in Java. So one way to get Java concurrency is you can extend this class thread and define a method run, or you have interface called runnable that you can basically use that interface and has a method run. And then when you we have a method run, and when in this runnable thread when you say start, that thread will get started. Okay, very simple ways to do that. Let me give an example. And a little bit of digression. Why do you want concurrent programming? A lot of times natural application structure is not sequential. The world is not sequential, and then try to sequentialize the world sometimes means it's much more complicated always. So sometimes it's natural to do things in parallel. In a lot of times the sequentiality is artifact of the programming language, because you use a language like that. And sometimes doing things in parallel ways, you can really improve things like throughput and responsiveness. So if you are doing I/O, if you do sequential programming, you need to do I/O just twiddling your thumb, waiting till the I/O to come back. Having parallel things, actually you can do parallel I/O, and you can do a lot of cool stuff in here. And of course, in this class, if you have multiprocessor and multicore, you can get parallel execution. So there are more than one to do that. I'm getting a phone call which I'm going to ignore. And also, if you're building a very large distributed system, that concurrent programming is you have to deal with, especially dealing with things like client server type application. So here's our original ATM. So to go to multiple ATM, I am doing few changes. So I will go back and forth few times. So the first thing I have done is I have set number of ATMs to be 4. Can you really read it from back there? Okay. Okay, good. Okay, and then what I have done is in here, I have added 4 ATMs here, and then I put it in a loop to create these ATMs. I create 4 ATMs in here and start 4 ATMs, basically. So and I of course extended this ATMs, now extend of thread class, and I have started that. And the ATM is as ATM, so it's great. So now what happens is, assume now there are 2 guys going, both ATMs, Alice and Ben, and they entered their account and they went. That works pretty well, no problem. So there are 2 ATMs, 2 people actually went in parallel. One Ben deposited some money, Alisa took money, great. Now, as MIT students, they want to do something they can hack it. So Alisa basically Ben went to both, and basically what it is, they enter the password, and they said, I want to get $100. I want to get $90 basically. So he had $100 in his account, and at the end, what he got was he actually managed to get $180 out of an account that had $100. Okay, this is not a good ATM, at least from the bank's perspective. So what went wrong? So if you look at what happened in activity trace, so we print 100 in here, and then you said you want to you read this value, both entered 90 and read here, and yes, is account balance plus val greater than 0? Yes, because the account balance was 100. This also did account balance plus val greater than 0? Yes, it is greater. And then each went post, it went to 10. This also did a post at the same time. The result came about 10. Okay, how could this happen? So the way it can happen is, so in the post code, what happens is V is 90, minus 90. And this post code also, when it started, V is minus 90. And then it reads the balance as 100. So this in this interleaving, and so it is the plus, you get 10. And also before you write it out, you read the balance in the other interleaving. It got the balance as 100, and you do the plus, it's 10. And so this wrote the balance. Now balance became 10, and also this guy also wrote the balance. Doesn't matter. It got 10 updated twice, and that's it. So you can have interleaving in here that actually did something that's not a sequential program. Okay, and you are in big trouble. So in order to get out of that, problem is all interleaving of thread are not acceptable and correct. Because what you want is some kind of a sequential looking performance, even though you would get parallel. You don't want you to do all these interleavings in here. So in order to do that, Java provides this synchronization mechanism that restricts interleaving. So what synchronizations do is it ensures safety for shared updates. So if you're sharing something, so it avoids races, basically it avoids this interleaving ordering in here. And also it allows you to coordinate actions among threads, basically, because at some point people have to coordinate, and things like parallel computation, when notification, you can do that. So when multiple threads access a shared resource simultaneously, it's safe only if all accesses have no effect on the resource. Basically, we are reading variables. You can read, everybody can read the same variable because you are not changing anything. I can do that. Or all accesses are idempotent. So you can say we can do that. Or only one access at a time, or which is called mutual exclusion. So in this case, we are changing something. It's not idempotent. So we have to actually do mutual exclusion. So here's a way to look at safety problem. Here might be an algorithm that you and your roommate have. So you arrive home, look in the fridge, no milk, leave for grocery, arrive at grocery, buy milk, and arrive at home. The minute you leave for grocery, your roommate arrives and do this. And at the end, what you have too much milk. So here's the problem in a little bit more abstract sense. And you need a way to synchronize this. So how about this? No milk and no note. So you leave a note before you actually leave the house and buy milk, and then you come back and remove note. Does this work? Okay. So
with thirst. Instead of starvation, you have thirst.
yeah, I mean here also you can do that. No milk and no note. So I guess okay, both are starting. I'm leaving note. And if these things can happen at the same time, there's a little bit of thing saying, okay, why didn't you see your roommate? But and they go buy milk, he goes buy milk, and you have too much milk too. So the way to do this in Java is this notion of critical section. If the critical section is where only one thread can be in it at a given time. And the way you can do it Java is you can put synchronize in front of the method. When you do that method, only one person can be executing that method at a given time. So in here, I will say get balance and post we can so synchronize. So when you do that, what happens is, so in here you read, no problem, you can do this parallel. You can do this in parallel. And then you say first account post in here, and this account post. And because of synchronized, these things can't happen overlap because this has to happen in some order. Either this happens first and this has to finish before this goes. And at that point, you can actually, what happened now? Are we happy? Yeah, at least bank realized bank's book is correct because it realized it gives more money, but actually it let you take more money than your account has. So at least it got the value right. But what happened was, why is this happening now?
You want to check also.
So okay, you want to check also. Okay, good. So so the key thing is here we didn't check. So you have a negative bank balance happening. So this is a problem of atomicity. Because synchronized method execute the body as atomic unit. So when that happens, the entire thing of body happens without anybody else modifying. That's the only thing that's happening at a given time. And the code region, the atomic unit you chose is probably too small in this case. What we need to do is we need to basically have synchronize in not on the method but a lot more code in there. So you have to do block synchronization. So synchronize keyword actually work like this too. So you can say, instead of doing a method, you can say synchronize account, and all those things happen synchronously within that part. Okay. So now what we have done is we have built a bigger atomic unit in here to do in there. So here's the program in here, and do I see the? Oops. So here's the synchronized unit in here. Okay. So what we did was we say instead of this synchronized and this synchronized separately, both this computation has to have atomic unit. So when I check and update balance, can't do anything else. So now what happens? So we are in this situation. You read in, and you get synchronized account in here, and I do account balance plus val and post the account. So in here I go to 10, I do that, and if I start the other one here, I have to wait till that entire synchronized region is over before I do that. Of course, I don't have enough balance, so I throw exception. Are we still happy? Is there an issue on this one? I mean, I guess assume you can do something clever, but I haven't done that. But there's one issue in here, which when you start, it says balance is 100. So in this one, say balance is 100. You go type it, and then voila, you type it, and at the end you say, oops, sorry, I don't have money. And so that's not nice, because if you have the balance, you should be able to get that. So how do I deal with that? Okay, so that's probably the best solution to that, because you can only log into one. But in this example, assume what we are doing. How can we deal with this one?
There are two ways of doing it. One is to put the whole thing inside a critical section. And the other way is to notify somebody that the file, like for example, when BI notifies that the file is changed.
Okay. So assume, okay, I will take the first approach. So what I can do is I can say, okay, wait a minute, I am actually going to make the critical section even bigger. So now I print the balance before I do that. So that entire thing is critical section. So I print the balance, ask, and then go and withdraw that. So what might happen in this case?
The other guy has to wait before he sees his balance.
Yeah, there's an issue of a little bit of waiting. So what happens is in here, you do this one, and you do synchronize account, and you put the balance, and the other one do synchronize, and you ask the question in here, and he start thinking. And the minute you start thinking, the other machine is not responsive because it's just waiting for the critical section to start. It can't, and you have this I/O event sitting in the middle. That's not good either. And so here's a performance issue. So that's not a good way of doing that. So you don't get any response in here. So you can make these atomic regions large, but there's a price you're paying by making atomic regions large. So here's another thing we want to do. I want to do something, I can transfer account balance from one account to another. Okay. So one way to do that is I have a method in here, say trans from to account this amount. So what I do is I say synchronize from account. I say get balance in here. If the balance is if the balance is available, I can synchronize the to account and post it there. See any problems? So let's see what happens. So assume Elisa want to transfer 10 to Ben's account, and Ben want to transfer 20 to Elisa's account. So what happens is this goes get the value in here, and you synchronize to 2, and you say okay, great. And now what happens is in here, in from, I am holding Elisa's account. There I am holding Ben's account. And now inside I want to synchronize for Elisa, and I'm saying, okay, wait a minute, I have to wait till Elisa got released, and he says I want to wait till Ben got released, and nobody's going to release, and you're hung. You are in what you call a deadlock situation. That's a deadlock. So you have to be very careful when you do synchronization. If you do multiple synchronization, okay, the easiest thing you can do is you do it in some order and you end up in a deadlock situation. This is a very common way of parallel programs to end up. So how do you avoid deadlock? Because deadlock is, there's a cycle in a locking graph. So somebody is going to lock somebody, he's going to lock that person, and when you have a cycle, you can end up in deadlock situation. So standard solution for that is you take locks in some kind of canonical order. Okay, you don't take in your arbitrary order. So it's some kind of a, you have some way saying, okay, if you are taking this lock, you have to have, after that you can't take a higher order lock. So you have to have some kind of order in here. Acquire, then you acquire in increasing order and release in decreasing order. So you have some kind of force in here. And this ensures deadlock freedom, and most of the time, but it's not that easy to do a lot of time, because your program might not fit into this nice ordering a lot of times, and then sometimes you realize that you have to lock something, and at that time it's too late when you realize it, and then it has a different order. So this is, you have to sometimes do some changes to basically make the program work like this. So in here, what you can do is, in the program, you can associate some kind of rank. And when you are putting accounts here, you put a rank to the account number. So you have some kind of ordering in here. And then what you have says, you always get the first highest rank one before you go to the next one. So there's some ordering in here. So Alice and Ben will be at least forced into some ordering in here.
Is there a way automatically to detect the deadlocks statically, like by program analysis?
Not statically. Because most of the time, that means you have to know all the kind of possible control flow paths to do that. And there are, for example, there are some tools that can, because you might know that, for example, assume you are trying to enforce some ordering of locks, but it's not, if the locking software doesn't know about the ordering, you can actually write a locking software that will tell you, like, look, you actually are trying to acquire lock in out of order, out of this locking order, and most of the time you might be okay because it might not hit, but we are saying, okay, you are doing some unsafe thing that might work. So you can put some dynamic checks that might warn you that you might be in situation, but it doesn't guarantee you. So deadlock is something you have to basically, there's no nice tools to do. So it's almost a software methodology. So for example, you can impose a software methodology to say, okay, I'm following this convention, and that will guarantee me deadlock freedom. So one good convention is this, basically some ordering here. So other interesting thing and hard thing is this race conditions. These are non-deterministic timing dependent and cause data corruption, crashes. It's impossible to detect. So the problem with race conditions is, the minute you put your debug, you run it on a debugger, put any debugging symbol, race conditions goes away. And it comes back when you have eliminated all any your debugging help. Well, it happens again because it's basically independent thing. In fact, I have this interesting experience myself. Long time ago, I was working at Microsoft, and I worked 2 summers. In one summer, I was working on their LAN manager, network manager, and there's a bug that after you run the network managers for some time, it just freezes. That's not a nice behavior to have for if you're running your network. And that bug lasted the entire year, and at the end they had, like, I think few $1,000 bounty on that bug, because the minute you do any instrumentation, bug doesn't appear. And when you remove all the instrumentation and have about 100 machines running heavily hitting another machine, once in a while, voila, the server freezes, and you have no idea what happened. And that was so hard to debug, because there's nothing you can do, because anytime you do any change, the bugs goes away. You have to be very careful, because these things are not easy to find and happen intermittently and very hard to debug. So having good discipline and good design really helps to get rid of it. These are not something you can go through like program, debug, iterate cycle, because if you hit that cycle, it's a very slow cycle. You have to get the design. The best way to do that is get the design right first. So what's a data race? So assume I have this program like that. So I read hits in there, and then I modify and write in this. This doesn't have to be in 2 statements. If even the same statement, the compiler might put it into register, read, update, and modify and write. So it doesn't. It might just look hits equals hits plus 1 and hits equals hits plus 1 other side too. It doesn't have to have temporaries in your code, because the compiler puts a temporary in there. And if you execute like this, you are happy. But if you get executed in this order, I don't get added 2 times. I only get because I read the original values. This add once and write, and this also add 1 to the original value and write. So I only get it increased by 1, and you are in a bad situation. And the problems with data races is this non-determinism. Okay, and we usually avoid that is mutual exclusion. So if you have same data access, make sure that they are in mutual exclude region, and you can basically serialize access to all the objects. So before you go that, so let's go that. One interesting thing is this is the problem with all parallel programs. So at the beginning you say, okay, I am going to have this nice mutual excluded lock ordered program. You write this thing. It works correctly beautifully, but run dog slow because now we have huge critical section. Everybody is waiting in data, and then someone says, I won't run fast. I think I don't need this lock. It doesn't seem to be. So you keep removing locks, making critical sections smaller and stuff like that. And that's where all the problems start cropping up, because all this nice design goes through the door when you have performance issues. So when you will realize that you're going to write these nice programs, nice large critical sections, stuff like that. Program will work correctly, but run like a dog because now it's sequential in many cases because you are doing that. And then you go and say, okay, I won't run parallel. This is okay. And that's when problems start creeping up. So make sure that when you get a discipline, that as you go into the performance improvement part, you still maintain at least some part of discipline, and that's the hard thing. So I want to switch gears a little bit to talk about a classic problem. It's called dining philosopher's problem. So there are 5 philosophers sitting around a table. Between each of philosophers, there's a chopstick. Okay. So each philosopher do 2 things. It thinks, he or she thinks, or he or she eats. So the philosopher thinks for a while, and then the philosopher is hungry. She stopped thinking and she pick up a left and right chopstick, eat, and put the chopsticks down. And he cannot eat until they have both chopsticks in hand, because you can't eat with one chopstick. And so you have to wait until you get both chopsticks. And when you're done, you put the chopsticks down. And then after you're done, you go back to thinking again for a while and come back to eating. So this is the classic problem. So how do you write that? We'll code that. Okay, you can have a philosopher extend thread, and assume you find philosopher, you have a chopstick in here, and you have you create instantiate a philosopher by left and right chopstick, and the main what you do is you create number of philosophers. And you get a new chopstick and start with the left, and you go to the other philosophers assigning left and right chopsticks in here, and then you start the philosopher going. So you get set up. So you set up a chopstick on it, and then you share the chopstick and do that. And then, so here's each what a philosopher does. So I am taking my left chopstick, I'm taking my right chopstick, and I'm going to eat, and I'm done eating, and I'm putting down there. What will happen in this one? I mean, what situation? He says starvation, whatever. That literally correct, but the right technical term is different. You end up in a deadlock, because if everybody pick up the left chopstick suddenly, and they all try to put a right chopstick, there's no right chopstick, and nobody has a right chopstick, and everybody waiting for somebody to drop the chopstick. That's not going to happen. So you have a problem. So the second way to solve that is this. You say, okay, the problem is everybody try to pick up a chopstick. I will put a unique variable table, unique object table, and if anybody want to eat, I need to own the table. What will this do?
Two people who wouldn't normally interact from eating at the same time.
Yeah. So what happens is only one person can eat at a time. So it works perfectly beautifully, but sequential. So even though if one philosopher eating, the person opposite can eat, but you are not allowed to because the chopstick in there. So one way of doing that is sequentialize large regions, basically putting these critical sections in there. This works, not greatly, but it will work. And the other thing is, of course, what I point out, so have some kind of ordering. So you put some position ordering and saying if you are in sitting in a even position, you have to first pick the left one. If you are putting an odd position, you have to first pick the right one. So in some sense, if you're sitting next to each other, you always go here, other person go here. So only one can get that. So you don't have ordering in here. So at least between those two, you can maintain that. So you can do something like you have to figure out what the right ordering in here. This is not a linear list, linear ordering, because this is a circle. But you can come up with ordering and say, okay, look, if you do that, there's no way you can run into a deadlock situation. So there are a lot of types of synchronizations in Java, and tomorrow you will learn a lot more different type of synchronization available in the cell processor using MPI. But there are a lot of potential problems you're worried about. Deadlock, you have to worry about 2 or more threads wait for each other forever. Live lock. What live lock means is 2 more threads basically trying to do something but never made forward progress. So good example. So assume I go, it's like sometimes you try to cross each other on a road, and so you go each other and you say, oops, sorry, you both move this way, oops, sorry, and both move this way. And you can be situation that you try to go something, both oops, sorry, move a little bit and then do that, and you keep doing that forever and never doing it right. So that can happen. So if you program right, you can actually try to avoid deadlock by doing that, but both are never making forward progress. So that's called a live lock. So another thing is called starvation. So the ordering is a very good example. So ordering says the higher order guy always gets the lock before the lower order guy. So assume you have thousands of things and everybody is trying to do something. And if you have a low order number, you probably never get around to get picked up, because always if higher order person has, that person will get the lock. So if they are ordering constraint in there, you can be in a situation that some people always get and others never get it, because there's no fairness in that, because when you have some ordering constraint. So again, lock fairness. And of course race conditions. So you didn't realize that the same object is accessed by multiple people without being inside a critical section. I think that's the key thing. I mean, don't try to do fancy things by letting multiple people have access to the same thing. This is not much of an issue on distributed memory machines, because there's no only you access to your memory. But the problem there is if you keep values, you suddenly start giving it to everybody and say, hey, go play, assuming that only one person have access to it. So multiple people might be modifying it, and then at the end, what are you going to do? So that issue is there. So when you're using data, you have to be very careful who owns the data and at what time. So concurrency and parallelism are important concepts in computer science beyond what we are doing in here. And concurrency can simplify programming and beyond anything. However, it's very hard to understand and debug concurrent program. That's the entire reason I think we are still doing sequential programming, and this is the entire reason that multicore people are looking at it in a people are scared, because writing and getting concurrent program right is probably order of magnitude harder than trying to get sequential programs right. So this is the issue. And parallelism is critical for high performance. I mean, it was issue for supercomputers at national labs, and now it's becoming everybody's issue because of multicore. And basically, you need to understand concurrency and concurrence issues. It's the basis of writing parallel programs. So you will run into all these issues, deadlocks. You can deadlock on not on memory access on cell. You can deadlock on messages. So everybody is waiting for somebody else to send you a message, and nobody is sending a message because they thought that other guy will send you a message. You can easily do that on a message in there, and a lot of times you can deadlock in that. And so this lecture we kind of did concurrent programming, how to write a concurrent program, and what we are going to switch gears and start going into parallelism next. But keep these issues in mind when you're writing parallel programs. Have things like Think 6170 we had very good discipline on testing and methodology of development. You probably won't have that kind of discipline on how to do parallelism. So there are many ways. Next few lectures will cover many different ways of doing parallelism. And parallelism is a very powerful tool, but But if you don't use it in a disciplined way, you will not be able to debug these things in 3 weeks. I mean, you'll run into bugs that are so subtle, so difficult, it's very hard to find. Because it's not, because you don't want in that situation. So having a good design, good discipline in programming will actually get you a working correct program. Good, that's all I have for today. And you can spend some time filling out this one. Just put your name down and when you're done, put it in here.